I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on wave propagation in lossy dielectrics for the course Electromagnetic Fields and Waves. And now we are going to see about the lossy dielectric. So, a lossy dielectric is a medium in which an electromagnetic wave, as it propagates, it loses power owing to imperfect dielectric. So, in other words, we can say a lossy dielectric is a partially conducting medium. It may be imperfect dielectric or imperfect conductor. In both the cases, we can call this as lossy dielectric, and it has the conductivity value sigma not equal to 0, which is distinct from a lossless dielectric where the sigma value conductivity is equal to 0. So a lossless dielectric is called as perfect or good dielectric, which has the infinite conductivity. And now we are going to see about the Maxwell's equations. So there are four Maxwell's equations we know. They are derived from Ampere's law, Faraday's law, Gauss law of electromagnetic and electromagnetics. And now these four Maxwell's equations form the basis for existence of electromagnetic waves in space. So according to Maxwell's equations, the equations are given as del dot Es is equal to 0, del dot H is equal to 0, del cross E is equal to minus j omega mu Hs, and del cross H is equal to sigma plus j omega epsilon into Es. So now we are going to take curl on both sides of the Maxwell's equation 3. So by taking curl, the left hand side of equation 3 becomes del cross of del cross E, and in the right side it becomes minus j omega mu into del cross Hs. Now we are going to apply a vector identity in order to further simplify this equation. The vector identity is del cross A is equal to del into del dot A minus del square A. So here del of del dot E is 0, and minus del squared Ey is equal to minus j omega mu into sigma plus j omega epsilon into Ey. So now this minus gets cancel both sides. We have del squared Es minus gamma squared Es is equal to 0, where this gamma squared parameter is equal to j omega mu into sigma plus j omega epsilon. So this gamma is called as propagation constant, and it is a very important parameter in describing the propagation characteristics of an electromagnetic wave when it is traveling through any type of medium. And this gamma is a complex term which contains the two important parameters. One is the attenuation constant and another one is phase constant. So the propagation constant of the medium is given as gamma. And now by similar procedure we have to apply to the magnetic field also. So similar to electric field equation, the magnetic field equation also becomes del square Hs minus gamma square H is equal to 0. So this gamma in the above equation, as I said already, it is a complex quantity. Alpha is the real part, beta is the imaginary part. So this alpha is called as attenuation constant and beta is the phase constant. So both these constants are constitute to the propagation constant, which describes the propagation characteristics of a medium. And now this alpha value attenuation constant for a lossy dielectric is derived, and it is the omega, the angular frequency, multiplied by square root of mu epsilon by 2, again multiplied by square root of 1 plus sigma by omega epsilon the whole square minus 1. And here beta equation is similar, but in the second term inside the second square root or second radical, instead of minus, the beta equation becomes plus. So these are attenuation constant and phase constant equations for a lossy dielectrics. So now the activity time. So a puzzle is given to you. So now we move on to how the wave is propagating through a lossy dielectric. The diagram explains the wave propagation characteristics of an electromagnetic wave traveling through lossy dielectric. So if we observe the graph, the attenuation constant and the wave amplitude decreases when it goes through the z-axis. So now we are considering the z-axis is the propagation axis. So initially the amplitude of the wave is high, and while propagating through a medium that is a lossless lossy dielectric, it gets attenuated. So from this we can understand that whenever an electromagnetic wave goes through a lossy dielectric, it's get attenuated or its amplitude decreases. So, as I said, the wave propagates along AZ, that is in Z direction. It decreases or attenuates in amplitude by a factor e power minus alpha z, and hence this is known as alpha is the attenuation constant or attenuation coefficient of the medium, and it is the measure of the spatial rate of decay of decibels per meter, and this will be given by the unit dB per meter. An attenuation of 1 Nepper denotes a reduction of e power minus 1 of the original value, whereas an increase of 1 Nepper indicates an increase by a factor e. So this 1 Nepper is given. So, and beta is the phase constant which describes the wave propagation characteristics. And now the assessment question. So, in the assessment question, a problem is given. A lossless dielectric has an intrinsic impedance of 230 ohms at a particular radian frequency, and if at that frequency the plane wave propagating through the dielectric has the magnetic field component H is equal to 10 into e power minus alpha z cos omega t minus 1 by 2 x ay amperes per meter. They are asked to find out the value of electric field and also the attenuation constant alpha. So, as we have observed from the characteristics of electromagnetic wave propagating through a lossy dielectric, we can easily find the value of electric field and also the attenuation constant from the given parameters. So, here the given parameters are the intrinsic impedance value eta is 200 and its angle 30 degree. So, the value is given in polar coordinates and the frequency is given, and the magnetic field equation is given H is equal to 10 into e power minus alpha z cos omega t minus 1 by 2 x ay ampere per meter. And here if the magnetic field is given, we can easily find out electric field by the expression the ratio of electric field to magnetic field is equal to the intrinsic impedance eta value. So here we know the eta value and also the magnetic field value. So we can easily find out the electric field. E is equal to H multiplied by eta. And similarly, from the previous attenuation constant expressions, we can easily find out the value of alpha also. So in this way, we can find out the answer for the given assessment question. Thank you.